Good morning. This is Kerry from Optic Wave Labs, and I'm going to try and describe reflective aluminum coatings in a couple of variations that we use for astronomy. So this is my design package called Film Star. It's a common industry thin film design, and this little section shows our visual range down here on the left, starting at 400 nanometers and going up to 750. So this is what we see as humans. And then on the left side of the graph here, we've got 0 to 100% reflectance. And there's no coating. This would just represent a non-coating or maybe a piece of glass. So the first thing we'll do is let's go and make this reflective. So what we're going to do is we're going to add a layer of aluminum. This would be pure elemental aluminum. And so we can see that in the chamber, our aluminum peaks out at 92% reflective. It's got this kind of arcing curve across the visual spectrum. Now, when we vent the chamber, this will immediately oxide and drop down to about 89% reflective. So that would just be a bare aluminum coating. We don't do those anymore. So now what we're going to do is try to protect this so it's not so soft. So let's go back to our layers here and let's add a little bit of silicon dioxide. All right, so we've got a layer over here on the right side. So just a little bit of silicon dioxide. It's not enough to protect it, but I'm starting it out low. And you can see as we'll go ahead and keep adding silicon dioxide. We'll see what happens to the curve. So our curve moves a little bit. Doesn't change too much. But what we do for our standard protected coating is we put 250 angstroms of silicon dioxide over the top of the aluminum. So let's dial this up close to 250. So you can see that silicon dioxide lowers the overall reflectivity in the chamber, but when we vent this, it won't oxide. And so we have about a 90% average reflectivity coating in a visual range. So that would be a standard coating. So now we talk about what's called a semi-enhanced, enhanced coatings. There's lots of mysteries. So to make a semi-enhanced coating, what we're going to do is we're just going to keep growing this silicon dioxide layer. And you'll see an interference wave starts propagating. I'm just going to slowly click this so you can see the action of how it would develop. So once the silicon dioxide builds up to a certain thickness, it has an interference property that acts as an anti-reflection coating. And so now we can see this swell is coming around here, and what we do is we try to optimize the ends of it here for the highest reflecting. So there's one end and there's the other end. So let's, right about there. So so now we've grown the coating to about 1800 angstroms thick, and you can see we have what's called a semi-enhanced coating. It's well protected, and it peaks out right over 550 nanometers at 92% reflective. The O3 region is 92% reflective. So that's a pretty good compromise on. We got a little bit more brighter coating with not much effort. And that thickness isn't too thick to cause too much scattering of light. All right, so now let's talk about the enhanced coating. So what we want to do to create an enhanced coating is put another dielectric layer on here with a different index of refraction, and it's called a high-low stack is what we're making. So if you notice there's an L, this is our low refractive index. I'm going to add the high. So let's go modify our design here. So I'm going to put this back to 799 angstroms, and then we're going to add 0.1. All right, so this is going to be titanium dioxide on the top. So now let's see as we increase that thickness, so we get another interference swell that moves across the coating design, just like we did before, but now we're adding that on top of the other interference. And we can optimize this little swell. somewhere in there. So the tail ends are about equal over here and here, and we're peaking out at around 96, almost 97% reflectivity in the peak visual range, and it's still not too bad in the blues and the reds. So that's our basic enhanced coating. We've added 799 angstroms thick layer of silicon dioxide and 595 angstroms thick layer of titanium dioxide. Now, one might think, well, hey, why can't I do that again? Let me add another low-high stack on top of here and boost the reflectivity again. And we can do that. So let's see what happens here. Let's just round these things up. We'll go 0.8 L and 0.6 high and 0.8 L and 0.6 high. And lo and behold, it actually works. So our peak reflectivity goes up to 98%, but you can see the ends of the curve start coming down. So we start losing some reflectivity in our extreme blue and extreme red, which isn't so bad. So, and you'll notice there is an optical coater out there that offers a 98% coating, and this is most likely what they're offering. They just put another interference stack on top of it, and it sacrificed the tail ends. Is that a good idea? I don't know. It might be. I've never actually looked through a coating like this. I might make one day and see. So that's basically how we come up with semi-enhanced and enhanced coatings on top of our standard coating. And what is interesting to note is this little combination here of these low-high stacks. This is actually how we build filters, optical filters, interference filters. And that's actually what we've done. We've built a very basic low-tech filter on top of our aluminum coating to increase its reflectivity.